Hopefully this didn't give you much trouble. However, one thing I know some of you are probably still doing at this point is choosing something like this. But note, we're looking for a displacement, and by definition, a displacement is a vector, and 8.06 meters is not a vector, so that cannot be the displacement. The correct answer is C, because we are taking the final, so minus 3I hat minus 5 gives minus 8I hat, and minus 3j hat minus 2j hat gives minus j hat. So let's see this with my motion across the room that we've been looking at as an example. I've superimposed two images so that you can see some initial and final position, and I've drawn in the displacement vector between them. And notice, as we expect, if I redefine where the axes are, the position vectors have changed, but the displacement vector hasn't. And the other thing to notice is that if I copy those vectors down below and flip the Ri around, you can see that Rf plus negative Ri gives delta R. So let's see how those same ideas play out in a position versus time graph. Here's the position versus time graph we got last lecture. And if I just pick 2 moments in time, I can read off the x components of position, right? That's what the vertical axis is showing here, x component of position. And I can just read those 2 x components off. And then the displacement, or rather the x component of the displacement, is just the difference between them. You can see how if I subtract xi from xf, I'll get that x component of displacement. But if I move the axes, in other words, if I redefine where x is 0, both of those x components of position have changed, but the x component of the displacement has remained the same, as we expect it to. Before we get to velocity, I need to point something out about time, and it's that it works sort of the same way. If we look at the times of those 2 instants that I picked on the previous graph, we can label them tf and ti, and we can read them off of the time axis. And there is some time interval, a difference in time, which we would just get by tf by ti. But our choice of when time was 0 was totally arbitrary, and so I could redraw my axes this way so that I've redefined when time is 0. Now note, both of those times have changed, but the delta t, the time interval, hasn't. And so just as we expect displacements to be more useful than positions, we should expect time intervals to be more useful than times. We're finally ready to tackle speed and velocity. So let's think about driving from Sydney to Halifax, which many of you will have done. Google Maps tells me that's 404 kilometers, and for me that drive would take about 5.5 hours. So we can say that my average speed would be 404 kilometers divided by 5.5 hours, and that's 73.5 kilometers per hour. Well, does that mean I went 73.5 kilometers per hour the whole way? Well, certainly not. As I was driving through Sydney, the police would have been awfully annoyed with me if I was going that fast. And on the stretch of the Trans-Canada between New Glasgow and Truro, everyone else would have been extremely annoyed with me if I was driving at that speed. The point is, this is the average, and aside from just thinking about speed, this also gives us a way of thinking about what average means. It's the constant value that would have the same effect as an actual varying value. The speed I was actually going was varying, but if I had gone at a constant 73.5 kilometers per hour, it would have had the same effect. I would have got from Sydney to Halifax in the same amount of time, assuming the police didn't pull me over. There are a lot of things about motions that we can just see by looking at graphs. So here is a position versus time graph. This is the x component of my position as I walk across the room. And I'm starting at x equals 1, and I'm ending at x equals 5. And the first one I'm going at what is for me a fairly relaxed walking pace. And you see I go 4 meters, right, from 1 to 5, in a time of 3 seconds. Now suppose I do the same thing, I start at 1 meter again, but I walk half as fast. Well, it should take me twice as long to go the same distance. So this graph here is me walking half as fast and taking 6 seconds to walk 4 meters. So this shows us right away, because the main difference between these is their slope, that a steeper slope means faster. And so that's something we can just see looking at a graph. The next thing to notice is that on this one, if you look at these two time intervals, which are the same time interval, I go the same displacement. And so that's saying in equal times I'm going equal distance, I must be going at a constant speed. And that's resulting in a constant slope. So this is how you recognize constant speed motion. If the slope is constant, then the speed is constant, and that's going to result in a position versus time graph that is a straight line. So that sets us up for next lecture, where one of the main messages is going to be that the slope of the x-component of position graph versus time is the x-component of the velocity.